In this lecture, we're going to look at transactions in MySQL. A transaction is a group of SQL statements that represent a single unit of work. So all these statements should be completed successfully or the transaction will fail. For example, think of a bank transaction. When you transfer $10 from your account to your friend's account, $10 should be taken out of your account and deposited into your friend's account, right? So here we have two operations, and these two operations together represent a single unit of work. Either both these operations should complete successfully, or if the first operation succeeds, but the second operation fails, we need to roll back or revert the changes by the first operation. A database transaction is exactly the same. We use transactions in situations where we want to make multiple changes to the database, and we want all these changes to succeed or fail together as a single unit. Let's say we want to store an order with an item in our database. We need two SQL statements to store this order, right? What if we insert the order record, but our server crashes at the time we're going to insert the order item? We'll end up with an incomplete order, and our database will not be in a consistent state. We don't want that. That's where we use transactions. Now, these transactions have a few properties that you need to know. The first one is atomicity, and this means our transactions are like atoms. They're unbreakable. Each transaction is a single unit of work, no matter how many statements it contains. Either all the statements get executed successfully and the transaction is committed, or the transaction is rolled back and all the changes are undone. The second property of transactions is consistency. And that means with these transactions, our database will always remain in a consistent state. We won't end up with an order without an item. The third property of transactions is isolation. And that means these transactions are isolated or protected from each other if they try to modify the same data. So they cannot interfere with each other. If multiple transactions try to update the same data, the rows that are being affected get locked, so only one transaction at a time can update those rows. Other transactions have to wait for that transaction to complete. And the last property of transactions is durability, and that means once a transaction is committed, the changes made by the transaction are permanent. So if you have a power failure or a system crash, we're not going to lose the changes. We refer to these properties as ACID. In the next lecture, I'm going to show you how to create a transaction. So you have learned that a transaction is a group of SQL statements that represent a single unit of work. In this lecture, we're going to create a transaction to store an order with an item. Now, before getting started, let's restore our databases so we work with the same data set and there are no surprises later in this section. So here's the script for recreating our databases. I'm going to execute this script. Beautiful. Now, back to our query window. Let's use our SQL store database. To create a transaction, we use the start transaction statement. Now, in this transaction, first we need to insert an order into the orders table. So, insert into orders. In this table, we have a few required columns: customer ID, order date, and status. Now let's set the values. I'm going to use 1 for the customer ID, 2019 January 1st for the order date, and 1 for the status. The values don't really matter. We just want to focus on this transaction. Next, we need to insert the order item. So, insert into order items. All the columns in this table are required, so let's just pass all the values. For the order ID, I'm going to use the last insert ID function. As I told you before, this returns the ID of the newly inserted order. Then I'm going to pass 1 for the product ID, 1 for the quantity, and 1 for the price. Again, the values don't really matter. Now here we have a syntax error because I forgot to put a semicolon here. Let's also terminate this line with a semicolon. Beautiful. Now finally, we need to close this transaction using the commit statement. When MySQL sees this command, it will write all the changes to the database. If one of the changes fails, it will automatically undo the previous changes, and we say the transaction is rolled back. Let me show you. So I'm going to execute this transaction. All right. Now let's take a look at the orders table. First, we need to refresh this view. All right. Here's the SQL Store database, and here's the orders table. So here's the new order that we created, order number 11. Also, let's take a look at the order items table. And this is the item for this order. All right, now let me simulate the scenario where this second statement is going to fail. So our transaction is going to get rolled back, and the change made by the first statement is going to get undone automatically. Let me show you. So on the top, under the query menu, we have this command, execute current statement. With this command, we can execute our script line by line. Now look at the shortcut. On the Mac, it's Command and Enter. So I'm going to put the cursor on line 3 and press Command and Enter. Now this line is executed, so we have a new transaction. Then put the cursor on line 5 and execute this line as well. Beautiful. Now we're not going to execute line 8. Instead, we're going to disconnect from the server. So I'm going to close this. This simulates the scenario where the client disconnects from the server. This can happen for a number of reasons. Maybe the client crashes, or the network goes offline, or the server crashes. It doesn't matter. Now, let's reconnect to the server and look at the data in the orders table. See what we have here. The last order is order number 11 that we successfully inserted earlier. So when we tried to insert order number 12, our transaction didn't complete. It was rolled back. That is why we don't have that order here. Okay? So most of the time, this is how we code a transaction. We have a start transaction statement on the top and a commit statement down the bottom. But there are situations that we may want to do some error checking and manually roll back a transaction. In those cases, instead of the commit statement, we use the rollback statement. Rollback. So this will roll back the transaction and undo all the changes. Now, one more thing before we finish this lecture. MySQL wraps every single statement that we write inside a transaction, and then it will do a commit if that statement didn't return an error. So whenever we have an insert, update, or delete statement, MySQL wraps this inside a transaction, and then it will do a commit automatically. This is controlled using a system variable called AutoCommit. Let me show you. So let's show variables like AutoCommit. There you go. We have this variable, AutoCommit, which is set to on by default. So whenever we execute a single statement, MySQL puts that statement in a transaction and commits it if the statement doesn't raise an error. So far, we've been the only user of our database. But in the real world, it's quite possible that 2 or more users will try to access the same data at the same time. This is what we call concurrency. Now, concurrency can become a problem when one user modifies the data that other users are trying to retrieve or modify. In this lecture, you're going to learn how MySQL handles concurrency by default. And then over the next few lectures, you're going to learn how to minimize concurrency problems. So we're going to simulate 2 users trying to update the points for a given customer at the same time. Let's go to the home page of MySQL Workbench and open a new connection to our server. Now we have 2 separate connections or sessions. In our first session, let's start a transaction. And by the way, we should make sure that we're using our SQL Store database. Okay? So we'll start a transaction and give customer number 1 10 extra points. So update customers, set points to points plus 10, where customer ID equals 1. And then we commit. Now don't execute this yet. Let's copy this entire code and paste it into our new session. Let me zoom in. All right, beautiful. Now, before executing this script, let's look at the customers table and see how many points customer number 1 has. So here's the customers table. Customer number 1 has currently 2,273 points. Now back to our first session. We're going to execute this script line by line. So using the shortcut that you learned earlier under the query menu, execute current statement, right? So let's execute the first line and then start a transaction and then update the points. but we're not going to commit. Now we go to our second session. Let me close the navigator panel. All right, here's the second session. In this session, we should also use our SQL Store database, start a transaction, and then try to update the customer. Now look at this spinner here. This update is running because when we executed the first update, MySQL put a lock on the customer row that we updated. So if another transaction tries to update the same row, it has to wait until the first transaction is complete, either committed or rolled back. That is why we had this spinner here. Now, this operation timed out. That's why the spinner disappeared. So I'm going to repeat this step one more time. In our second session, I'm going to start a new transaction, update the customer. Okay, it's waiting. Beautiful. Now back to our first session. Let's commit the changes. All right. Now let's go to the second session. Update is no longer running, so it affected one row, but the changes are not committed yet. Let's commit the changes. All right. Now, back to our customers table. Let's refresh the result and look at the points for customer number 1. We have 20 extra points here because each transaction increased the points by 10. So if a transaction tries to modify a row or multiple rows, it puts a lock on these rows, and this lock prevents other transactions from modifying these rows until the first transaction is done. Either it's committed or rolled back. So with the default lock-in behavior in MySQL, you don't have to worry about concurrency problems most of the time. But there are special cases where the default behavior is not sufficient for specific scenarios in your applications. In those situations, we can override the default behavior, as I will show you shortly. Next, we're going to look at the common concurrency problems and how to solve them. Now that you know what concurrency is, let's look at the common problems it brings. The first problem is lost updates. This happens when two transactions try to update the same data and we don't use locks. In this situation, the transaction that commits later will override the changes made by the previous transaction. For example, let's say that we have two transactions that try to update the same customer. One tries to increase the points, the other tries to update the state for this customer. Here's our customer record. John in New York with 10 points. Now we have two transactions. Transaction A that tries to update the state of this customer, and transaction B that tries to update the points for this customer. These two transactions occur at the same time. This is the customer record that both these transactions see. Now, let's say transaction A updates the state, but it hasn't committed yet. At the same time, transaction B updates the points. Now, the transaction that commits last will overwrite the changes made earlier. In this case, if transaction B commits last, we will lose the update made by transaction A. How can we prevent this from happening? We use locks. So as you saw in the last lecture, by default, MySQL uses a lock-in mechanism to prevent two transactions from updating the same data at the same time. They will run in sequence one after another and will have both updates. Let's look at the next common concurrency problem, dirty reads. A dirty read happens when a transaction reads data that hasn't been committed yet. For example, transaction A changes the points for a customer from 10 to 20, but before it commits the change, transaction B reads this customer and based on the customer's points makes a decision. Let's say for every 1 point, it gives a $1 discount to the customer. So it's going to give this customer a $20 discount. Now, what if transaction A rolls back before transaction B completes? Transaction B would have data that had never existed. In other words, this customer never had 20 points, this was never committed to the database, and transaction B gave this customer a $20 discount. So in this scenario, we have read uncommitted data in transaction B. Our data was dirty. Now, to solve this problem, we need to provide a level of isolation around our transactions. So data modified by a transaction is not immediately visible to other transactions unless it's committed. The standard SQL defines 4 transaction isolation levels, which you're going to learn about soon. One of these is read committed. When we use this isolation level for a transaction, that transaction can only read committed data. With this, we won't have dirty reads. Now, what if the data gets changed after our transaction completes? It doesn't really matter. What matters is that any data that we read is committed at the moment it is read. If we make a business decision in a transaction, we base our decision on valid, committed data. The data can change later after the transaction, and our transaction shouldn't worry about that. So when we set the isolation level for a transaction to read committed, that transaction will only read committed data. In the next lecture, I'll show you how to set the isolation level. Now let's look at another concurrency problem, non-repeatable reads. So by adding more isolation to our transaction, we can guarantee that our transaction can only read committed data. But what if during the course of a transaction, we read something twice and get different results? For example, transaction A reads our customer's points. It sees that this customer has 10 points, so it will make a business decision based on this value. Now, before transaction A completes, another transaction, like transaction B, updates the points for this customer to 0. Now, back to transaction A, we read the points for this customer one more time, perhaps as part of a subquery. Now, in this transaction, we have read the points twice, and each time we have seen a different value. This is a non-repeatable or inconsistent read. How should we handle this situation? Well, we can argue that at any point in time, we should make decisions based on what is the most up-to-date. If that's the case for a business scenario, we don't really have to worry about anything here. But we can also argue that at the time our transaction started, this customer had 10 points, so we should have given them a $10 discount. If the points change during this transaction, we shouldn't see the changes. We should see the initial snapshot. If that's what we want, then we need to increase the isolation level of our transaction. We need to isolate it from other transactions such that changes to the data aren't visible to our transaction. The SQL standard defines another isolation level called repeatable reads. With this level, our reads are repeatable and consistent, even if the data gets changed by other transactions. We'll see the snapshot that was established by the first read. And the last common concurrency problem is phantom reads. Imagine in transaction A, we're querying all the customers who have more than 10 points. Perhaps we want to send them a special discount code. Now, at the same time, transaction B updates the points for another customer that was not returned by our query. So this customer is now eligible for this discount code, but at the time we queried the customers table, we didn't see this customer. So after transaction A completes, there is still one eligible customer that didn't receive this discount code. This is what we call a phantom read. Phantom means ghost. So we have data that suddenly appears like a ghost, and we miss them in our query because they get added, updated, or removed after we execute our query. How can we solve this problem? Well, it depends on the business problem we're trying to solve and how important it is to include this customer in our transaction. We can always re-execute transaction A at a later time, and this customer will also get a discount code. Not a big deal. But if it's absolutely critical to include all eligible customers in our transaction, we'll have to make sure that no other transactions are running that can impact our query to find the eligible customers. For this, we have another isolation level called serializable, and this will guarantee that our transaction will be aware of changes currently being made by other transactions to the data. If there are other transactions modifying the data that can impact our query result, our transaction has to wait for them to complete. So transactions will be executed sequentially. This is the highest level of isolation that we can apply to a transaction, and it gives us the most certainty in our operations. But it comes with a cost. The more users and concurrent transactions we have, the more waits we're going to experience, and our system is going to slow down. So this isolation level can hurt performance and scalability. For this reason, we should reserve this only in scenarios where it's absolutely critical and necessary to prevent phantom reads. Now, if all this sounds overwhelming, don't worry. We're going to review all these concurrency problems and how to solve them again. Later in this section, I will show you each concurrency problem and how to solve it using a transaction isolation level. In the last lecture, you learned about common concurrency problems and how we can prevent them using standard transaction isolation levels. In this lecture, we're going to review these isolation levels one more time, and I will summarize everything for you in a way that you can easily remember. Let's start by reviewing the concurrency problems. We have lost updates, which happens when two transactions update the same row, and the one that commits last overwrites the changes made earlier. We have dirty reads that happen if we read uncommitted data. Another problem is non-repeating reads, which happen if we read the same data twice in a transaction but get different results. And phantom reads, which happen when we miss one or more rows in our query because another transaction is changing the data and we are not aware of the changes in our transaction. We're dealing with phantoms or ghosts. Now, to solve these four problems, we have four standard transaction isolation levels. Read uncommitted, which doesn't really protect us from any of these problems because our transactions are not isolated from each other and they can read uncommitted changes by each other. Next, we have read committed, which gives our transactions a bit of isolation so we can only read committed data, and this prevents dirty reads. But at this level, it is possible that during a transaction, we read something twice and we get different results because another transaction updates the data in between the two reads. So it doesn't really protect us from non-repeatable reads. That brings us to the repeatable reads level. At this level, we can be confident that multiple reads return the same result, even if the data gets changed in the meantime. And finally, we have serializable, which prevents all these common problems. With this level, we can prevent phantom reads, so if data is getting changed in the meantime, our transaction will wait to get the most recent data. Obviously, this puts an overhead on the server because it needs extra resources in terms of memory and CPU to manage the transactions that have to wait. So the more we increase the isolation level, the more performance and scalability problems we're going to experience because more locks will be involved to isolate transactions. So to recap, a lower isolation level gives us more concurrency, so more users can access the same data at the same time. But more concurrency means more concurrency problems. On the flip side, we achieve a better performance because we need fewer locks to isolate transactions from each other. A higher isolation level restricts concurrency, and that means fewer concurrency problems, but at the cost of decreased performance and scalability because we need more locks and resources. So the fastest isolation level is read uncommitted because it doesn't set any locks and it ignores the locks set by other transactions. For this reason, we may experience all concurrency problems. As we go down this list, we get better protection from the concurrency problems, but that also means we're going to use more locks, and this requires more resources, which can hurt performance and scalability. In MySQL, the default transaction isolation level is repeatable reads, which works well for most scenarios. It's faster than serializable and prevents most concurrency problems except phantom reads. So stick to this unless you absolutely have to prevent phantom reads for a specific transaction. In that case, you can use the serializable level for that particular transaction. As for the other two isolation levels, read committed and read uncommitted, you can use this in situations such as bulk reporting where you don't need precise consistency or when you deal with data that is rarely updated and you want to achieve a better performance. Again, I would say stick to the default for most scenarios and only change the isolation level if you really have to. Now let me show you how to set the transaction isolation level. First, let's view the current isolation level. We're going to use the show variables statement to view the system variables used by MySQL, and then we're going to filter the list to only see a variable called transaction underline isolation. There you go. So the current transaction isolation level is repeatable read. This is the default in MySQL. Now to change the transaction isolation level, we use the set transaction isolation level statement, and then we type the name of the new isolation level, such as serializable. This will set the isolation level for the next transaction. We can also set the isolation level for all future transactions in the current session or connection. So we add the session keyword here. So as long as we have this session or connection open, all the future transactions will have this isolation level. We can also set the isolation level globally for all new transactions in all sessions. And for that, we use the global keyword. Now, if you're an application developer, you have a function or method somewhere in your application that connects to your database to execute a given transaction. You may use an object relational mapper or directly connect to MySQL. Either way, just before executing your transaction, you change the isolation level only for that session or connection, and then run your transaction. So you connect to MySQL, change the isolation level, execute your transaction and disconnect. This way, other transactions in the database will not be affected. All right, that brings us to the end of this lecture. We're going to see each of these isolation levels in action. In this lecture, you're going to see the read uncommitted transaction isolation level in action. If you want to follow along with me, do it exactly like what I'm going to show you, so there are no surprises later on. First, I'm going to close both these sessions because I want to start from a blank canvas. So let's open a new connection. This simulates one client. Now let's open another connection. And here's our second client. Now in the first session, first, let's use the SQL Store database. Then we're going to set the transaction isolation level to read uncommitted. With this isolation level, we'll be able to read uncommitted data. So we're going to have dirty reads. Then let's select points from the customers table where customer ID equals 1. Now let's go to the second session. Here, once again, we're going to use the SQL Store database. We're going to start a transaction. And in this transaction, we're going to update the points for this customer. So update customers, set points to 20, where customer ID equals 1. And finally, we're going to commit. Now, before executing any of these scripts, let's look at our customers table and see how many points this customer has. So here's our customers table. Our first customer has 2,293 points. Beautiful. Now let's go to the first session. We're going to execute line 1. Then we're going to set the transaction isolation level. So the next transaction is going to have this isolation level. But here we don't have a start transaction statement because, as I told you before, every single statement that we execute, MySQL wraps that statement inside of a transaction and automatically commits that. Now here we're not modifying any data, but this select statement is still executed inside of a transaction. Okay? Now, we're not going to execute this line. Instead, we're going to go to the second session. First, we're going to use our SQL Store. Then we're going to start a new transaction and update the points for this customer. Now, we haven't committed the changes at this point, but if we go back to the first session, because we set the isolation level to read uncommitted, this select statement will read uncommitted data. Take a look. So execute. Now we have 20 points, but as you saw earlier, this customer should have 2,293 points. Now here's the problem. In this transaction, we are reading the points as 20. We might make a decision based on this value, but what if in the first transaction, this commit never happens for whatever reason? Maybe the server crashes or the transaction explicitly rolls back. So let's roll back. Now, in our first transaction, we're dealing with a value that never existed in the database. This is the problem with dirty reads. So to recap, read uncommitted is the lowest isolation level. And with this level, we may experience all concurrency problems. In this lecture, you're going to see the read committed isolation level in action. So you saw the problem with dirty reads in the last lecture. Now we're going to change this isolation level to read committed. So read committed. With this isolation level, we can only read committed data. So we're not going to have dirty reads. Now, before executing any of these scripts, let's double check what we have in the customers table. So I'm going to refresh the result. Customer number 1 has 2,000 points. All right, now back to the first session. Let's execute line 2 to set the isolation level. All right, now back to the second session. Once again, we're going to start a new transaction. We're going to update the customer's points to 20, but we haven't committed anything yet. So if we go back to the first session and read the points, we should not see that uncommitted data. Take a look. Select points. We have 2,293. Now back to the second session. If this transaction is committed, let's commit it. Now our customer has 20 points. So we go to the first session, read the points again, and now we have 20 points. Beautiful. So at this isolation level, we don't have data reads, but we have another problem. We have unrepeatable reads. So it is possible that during a transaction, we read something twice, but we get different values each time. Let me show you. So here we're going to start a transaction because we're going to have two select statements. So start transaction. Here's our first select statement. I'm going to copy paste this one more time and then commit. Now for clarity, I'm going to compress this select statement into one line like this. So we have two select statements. That's better. All right, now once again, we need to execute line 2 to set the isolation level because this only applies to the next transaction. We already had a transaction with this isolation level. So this new transaction is not going to have the same isolation level. It's going to have the default isolation level, which is repeatable read. So let's execute line 2. All right, now we start the transaction. We read the points. There you go. We have 20 points. Now, before we execute the next line, we're going to go to the second session and update the points to, let's say, 30. So here we're going to start a new transaction, update the points, and then commit. Now, if you go back to the first session and read the points again, we get a different value. So at this isolation level, we have non-repeatable or inconsistent reads. To solve this problem, we need to increase the isolation level for this transaction, and that's what I'm going to show you next. In this lecture, you're going to see the repeatable read isolation level in action. With this isolation level, our reads are going to be consistent and repeatable. Let me show you. Now, the first thing we want to do here is to commit the transaction from the last lecture. So we can come back and change the isolation level for the next transaction, okay? So commit this, nothing happens. That's perfectly fine. Now let's change the isolation level to repeatable read. All right, now let's execute line 2. Then let's start a new transaction. We're going to read the points. So currently we have 30 points. Now before we execute the next line, let's go to the second session and change the points for this customer to 40. So we're going to start a transaction, update the points, and commit. Now back to the first session. When we execute the next line, we're going to see the same value. Take a look. We got 30, so our reads are repeatable and consistent. So this is the benefit of this isolation level. And by the way, as I told you before, this is the default isolation level in MySQL that solves most of the concurrency problems. But at this level, we have one problem, and that is phantom reads. So let's change our query to get the customers located in Virginia. Perhaps we want to give these customers a special discount. So we're going to select everything from the customers table where state equals Virginia. Now, we don't really need to repeat this query, so let's delete line 5. So if we execute line 4, we see customer number 2 as the only customer who is located in Virginia. Now, to start a new demo, let's commit this current transaction. All right, done. All right, now we're going to start another transaction. But before selecting the customers, let's go to the second session and set the state for customer number 1 to Virginia. This customer is not currently located in Virginia. So the scenario that we're simulating here is that one client tries to read the customers that are located in Virginia. And at the same time, another client is updating the data such that this customer, customer number 1, should be included in this query that client number 1 is executing. So here in the second session, let's start a transaction, update the customers. Now we're not going to commit anything yet. This is just a pending transaction in memory. So technically, this is not written to the database. So if we go back to the first session and read the customers, obviously we're only going to see customer number 2. Now at this point, the second session is going to commit the changes. So now we have 2 customers located in Virginia, but we missed one of them, customer number 1. If you read this customer again one more time in this transaction, we're going to see the same result because with repeatable read, our reads are going to be consistent. So we'll have to commit this transaction. Now, if we read these customers one more time, we can see We have 2 customers in Virginia, but we missed one of them. This is what we call a phantom read. In the next lecture, I'm going to show you how to use the serializable isolation level to solve this problem. In this lecture, we're going to look at the serializable isolation level, which provides the highest level of isolation and solves all concurrency problems. So at this level, our transactions are executed in sequence, one after another. So we really don't have concurrency. The experience we get is like a single user system. One user executing different commands against the database. These commands are executed sequentially. Now, following the example from the last lecture, let's execute line 4. So currently we have only 2 customers in Virginia. Now we're going to change the transaction isolation level to serializable. Let's execute line 2. All right. Now we start a new transaction. But before we read the customers in Virginia, let's go to the second session and add another customer in Virginia. So customer number 3. So we start a transaction. We update the customers. We haven't committed anything yet. So while the first client is trying to read the customers in Virginia, another client is updating customer number 3. So this customer should be included in our query. Otherwise, we're going to have phantom reads. So I'm not going to commit this transaction yet. Instead, we're going to execute line 4. Now, look at this spinner here. This transaction is waiting for this other transaction to finish. This is the result of serializable isolation level. So once we commit this, then our transaction will execute, and now we have 3 customers in Virginia. So with the serializable isolation level, we solve all concurrency problems. We don't have phantom reads. We don't have lost updates or dirty reads. All concurrency problems get resolved because our transactions are executed sequentially, one after another. The more users and the more concurrent requests we have, the more waits we're going to experience. So as I told you before, use this isolation level only for situations where you want to prevent phantom reads, but not for every transaction in your system. The default isolation level, that is repeatable read, works for most scenarios. So stick to that unless you know what you're doing. All right, now let's look at a classic problem in databases. Deadlocks. What is a deadlock? A deadlock happens when different transactions cannot complete because each transaction holds a lock that the other needs. So both transactions keep waiting for each other and never release their lock. Let me show you. So here in MySQL Workbench, I'm going to close both these sessions and start over. I want to make sure there are no surprises. We start from a clean canvas. So let's open a new connection. And one more time. Now in our first session, we're going to use our SQL store database. Then we're going to start a transaction. In this transaction, we're going to update 2 records. First, we're going to update the customers table and set the state to Virginia for customer number 1. So where customer ID equals 1. Let me zoom out a little bit. That's better. Then we're going to update the orders table and set the status of an order to 1, where order ID equals 1. Now, don't worry about these values I've used here. It doesn't really matter. What matters is that first we're updating 1 record in the customers table, and then we're updating 1 record in the orders table. Okay? And finally, we're going to commit here. Now, before executing the script, let's copy this entire code and paste it into the second session, like this. But here in the second session, we should change the order of these update statements. So we update the orders table first and then the customers table. I will explain why this matters shortly. Now back to the first session. In this transaction, when we execute line 3, we're going to update customer number 1. This transaction will put a lock on this record, so other transactions will not be able to update this record, right? They'll have to wait. And this doesn't matter what isolation level we use. Earlier in this section, you learned that whenever we try to update a record, MySQL puts a lock on that record, so other transactions have to wait. So here we try to update this customer, but let's imagine, before line 4 is executed, another user starts a new transaction at the same time. This user is going to update one order in this table, order number 1. So this transaction is going to put a lock on this record. Then this line is about to get executed. So we try to update the same customer that the other transaction updated. So transaction number 1 already put a lock on this record. So we cannot complete this transaction. We'll have to wait for that transaction to complete. Okay. Now we go back to the first transaction and execute line 4. At this point, we try to update order number 1, but transaction number 2 already put a lock on this record. So we'll have to wait for that transaction to complete. Here's the problem. Both these transactions are waiting for each other and they will never be able to complete. This is what we call a deadlock. So let's see this in action. Here in the first session, let's execute the first statement. Then we're going to start a transaction. We update the customer. Now we go to the second session. And once again, use our SQL Store database. We start a new transaction. We update the order. So far, so good. Now we update the customer. This transaction is waiting. Take a look here. So we go back to the first transaction and execute line 4. Now we get a deadlock. So if you look at the output window, you can see an error here. Error 1213, deadlock found. In this situation, MySQL treats this transaction as the victim and rolls it back. So this is how a deadlock happens. Generally speaking, deadlocks are not a big issue unless they happen so frequently. If you're an application developer, you should write your application in a way that it can reissue a transaction if it gets rolled back because of a deadlock. Or you may just tell the user, hey, this operation failed, please try again. But there are a few things that you can do to minimize deadlocks. You can never completely get rid of them, you can just minimize their likelihood. Here are a few things. If you frequently detect deadlocks in 2 transactions, look at their code. These transactions could be part of 2 stored procedures. Now look at the order of the statements in your transactions. If these transactions update records in the reverse order, it's likely you're going to have a deadlock. That is the reason we swapped the order of these statements in the second session earlier. So to reduce deadlocks, you can follow the same order when updating multiple records. That's one solution. The other thing you can do is to keep your transactions small and short in duration, so they're not likely to collide with other transactions. If you have transactions that operate on really large tables, these transactions may take a long time to run, and then you're at risk for collision. If that's the case, see if you can schedule those transactions to run during the non-peak hours when there are not a lot of active users. So that's pretty much what you can do. And that brings us to the end of this section. If you found this section a little bit overwhelming, I totally understand. Quite honestly, concurrency is a fairly advanced topic, and it's okay if you're confused the first time you're learning about it. I personally had the same experience myself, and I had to look at several different sources to really understand concurrency. Trust me, you're not going to find any books or videos that simplifies this concept for you the way I've done in this section. I've worked really hard on this section to make it super simple for you. So if you're confused, just take a break and watch this section again from the beginning. I promise you're going to digest everything I've explained. All right, that's it for now. I will see you in the next section.